Okay, the ball has a mass of 270 grams, which I'll convert right away to kilograms. The initial velocity is 10 meters per second down. Now I assume that after the person bumps the ball is going to be going up. So I'm looking for a final answer to be in the up direction. V2 is a question mark. So I know the starting momentum of the ball. I can calculate that. I do not know the final momentum of the ball. However, I can use the graph here to calculate the impulse. The area of this graph, it's a force versus time graph. So the area of the graph is going to give force times time, which is impulse. Okay, so I'll calculate that right away. It's the area of this. The shape is a triangle, so it's a half base times height. So the base it goes from 0 to 0.020 seconds. So the base is 0.020 seconds. And the height goes from 0 to 450 newtons. So the height is 450 newtons up. I know it's up because I read the y-axis and it says up. So I calculate that. I believe that would give 4.5 Newton seconds, or that's the same as our units of momentum, kilogram meters per second up. Okay, so that's our impulse. I'll just add that to my list here, my net impulse. Will be that. I'm thinking that, well, I mean, that's the impulse from the bump. That's the impulse from the bump. Because that graph only gives the force of the bump. What about the other forces acting on the ball? So, I mean, there would be gravity. So, yeah, I'm going to have to, well, we'll see if we have to take that into consideration here. The net impulse has to be all the impulses added together. So the impulse from gravity, J gravity, would be the force of gravity times time. The force of gravity is mg times time. So that's 0.270 kilograms, 9.8 newtons per kilogram. And the time, it's the same as the time of the bump, which is 0.020 seconds. So calculating that, let's see what we get. We get 0.053 kilogram meters per second down, because gravity is down. So does it matter? It's not gonna matter by much. If you compare that versus the 4.5, it's very, very small. Okay, so I don't think it will actually affect the answer. But you know what? Since we calculated it, let's just get the whole thing. So the net impulse would be the impulse from the bump plus the impulse from the gravity. That would be 4.5 plus negative, because it's gravity one's down, negative 0.053. That will be 4.447 to one decimal place. Okay, so that's the net impulse. In my list on the left, I want to make sure everything's in the same direction. I'm going to make up my main direction. So I'm going to change the V1 to negative 10 meters per second up. Okay, now I will apply the impulse momentum formula. Delta P equals net impulse. P2 minus P1 equals net impulse, which we know is 4.447. mv2 minus mv1 will equal to our net impulse. I can divide both sides by m. Divide both sides by m and then add v1 to both sides. That will get me my v2. Okay, so that's what I'll calculate. This is negative 10 meters per second plus 4.447 over 0.27. Okay, let's figure out what that is. That will end up being positive 6.5. Okay, I wonder if I calculated without gravity, what the answer would be. Like, what if I just ignored gravity and just used 4.5 here, okay? Only used the impulse I got from the graph. Can I recalculate that? I do get a different answer. I get 6.7. Okay, so yeah, it was a good thing that I remembered to include gravity into this calculation. Okay, it'll be just 0.2 meters per second slower if we take into account gravity. That's going against the bump force.